Lesson number 81 is about graphical solutions, inconsistent equations, and dependent equations. Now, our questions are going to ask us to do this. We need to solve by graphing. And when we solve this by graphing, this is a system, so we'll have our brace here between our two equations. The first one is y equals x plus 1. Well, we know when we have an equation like this, we can write it in slope-intercept format, y equals mx plus b. And we want to graph our b value first. So for our first equation, y equals x plus 1, we're going to graph the 1, because that's our y-intercept, the b value. And then our slope here, well, is a 1. So that means up 1 over 1. Up 1 over 1, up 1 over 1, up 1 over 1, and so on. So we can see what our line is going to look like. Now I'm going to make a few more points so we can make a nice straight line. Points should go through all of our points as precisely as possible. Use a straight edge when you do this. And then we've got our first equation, and it's all done. Our second equation, we need to graph the line y equals negative 2x plus 4. So for this one, we'll use red. Y equals negative 2x plus 4, so 4 is our y-intercept. And then we go down 2 over 1 for our slope. Down 2 over 1, down 2 over 1, down 2 over 1. We'll do it one more time. Down 2 over 1. Now we can go ahead, nice straight line through these points. We make a nice straight line through these points. There we go. That looks good. We'll add our arrowheads because this is a line and not a segment or array. Now what we need to do when we're solving this by graphing is looking for where the two lines intersect. And we can see the two lines, they must intersect right here. That's where the red line and the orange line cross. And that point is going to be 1 on the x and 2 on the y. So that's our answer. X equals 1 and y equals 2. And we can write that as a coordinate pair, 1, 2 in parentheses, and we're all done with this problem. The key here is to make sure you graph them accurately. Use straight lines so that you can find your answer. Let's look at another one. Let's solve by graphing again. So first we have y equals 2. So if we have y equals 2, that means all y values are 2. Here's 2 on the y. Here's a 2 on the y. All the way across would also be a 2 on the y. So let's take our straight edge. And we've got our first line, y is equal to 2. This is our blue dot. Then y is equal to x. So if y is equal to x, that must mean that whatever x is, y will be the same. So if x is 1, y is 1. If x is 2, y is 2. And we actually just found our answer. We found our answer. We could continue graphing this. We know what it's going to look like. It's going to have a positive slope. And it's going to be up 1 over 1. So we can extend it out a little further. Whoops, we don't want to use our blue color here. And using a nice straight edge, we can see exactly where our points of intersection will be. This one, we have 1 point of intersection again, and our point of intersection is 2 on the x and 2 on the y. So our answer is going to be 2, 2. 2 on the x and 2 on the y. And we're all done with this second problem as well. Let's look at another example. Here we want to solve by graphing. First one, y equals x plus 2. So if y equals x plus 2, we have 2 as our y-intercept, and then our slope is up 1 over 1. Up 1 over 1, and we can just go diagonally across because we know exactly what this one's going to look like. Use a nice straight edge, and we can figure out exactly where this will work. We want to put our arrowheads on, and we can move on to our next equation. Y equals x minus 1. So if we have y equals x minus 1, our y-intercept must be negative 1. And then our slope is, well, our slope is the same. It's up 1 over 1. So again, up 1 over 1. We can go all the way across. Now we'll take out our straight edge. And what you can see here is that when we have our two straight lines, they just look like railroad tracks. In this problem, there is no point of intersection. So this example has no solution. And that's what we'll call it, no solution, because they will never intersect. Let's look at one more. Here we have y minus x equals 2 and 2y minus 2x equals 4. So we need to solve both equations for y. In order to do that with our first equation, we need to add x. So that's going to turn into, when we add x to both sides, y equals x plus 2. And let's graph that. We go up 2 for our y-intercept. We go up 1 over 1 for our points. So we can draw a nice straight line. All right. Now add our arrowheads because we're working with a line here. And now our second equation, the reason this one is different is because we have to rearrange. So if we're going to rearrange with this equation, let's solve for y. And if we solve for y, we can see we're going to get, well, we're going to add 2x to both sides. So if we add 2x to both sides, and let's use a different color, plus 2x plus 2x, this is going to turn into 2y is equal to 2x plus 4. Then in order to figure out what y is, we have to divide everything by 2. So if we cut everything in half, y is going to equal x plus 2, because we cut everything in half by dividing each by 2. We now have the same equations, y equals x plus 2 in blue, and y equals x plus 2 in red. So that means wherever we had our blue dots, we now have our red dots. And our red line is going to be right on top of our blue line. Even though the equations didn't look the same in the beginning, we know that they are when we solve them to simplify and solve for y. So what we call this is infinitely many solutions. Because every point on both lines touches another point from the other line. Infinitely many solutions will be the way that we'll answer this question. Now, when we answer these, there's different ways. If we have one ordered pair, like the lines cross at just one point, and that one point would be right here, we could call them one solution and give it, like the xy coordinate pair, or we could call them consistent equations. Inconsistent equations when there are no solutions. So that's like our railroad tracks. They're never going to touch each other. And we'll make sure that they look like they're never going to touch each other. They're parallel lines. And for dependent equations, infinitely many solutions, well, that's when we would have one line that is right on top of the other line. And we can call that infinitely many solutions or dependent equations. It's your choice if you want to answer them using consistent, inconsistent, or dependent, or one solution, no solution, or infinitely many solutions. Remember, if it's one solution, we want to give what that solution is as an xy coordinate pair. For the other two, we can't. Our lesson practice will be on page 335. Make sure you've got your notes complete, and I'll see you during our next class.